Postdoc van de universiteit in Sweden is going to be Big Brother logic, logical framework for multi-page visual-epistemic reasoning.
Thank you. Good morning to everyone. Before I start, first some special words of thanks. This is my first visit to Brazil, or to the whole of South America, and therefore my first visit to the beautiful city of Natal. So I would like to use the opportunity to thank very much the organizers, and in particular João and Eleni and Carlos, and everyone else who organized this lovely conference. I'm really excited to be here and to give this talk, so thank you. Okay, so the story that I'll be talking about is, well, yeah, I should say one more thing. I have gradually realized, especially yesterday, that proof theory reigns supreme here in this conference and in this place. So that I'm a bit uneasy and a bit worried that I might disappoint you with this outrageously semantic talk that I'm going to give here, almost proof theory free. But I hope that you will still enjoy it, even though it's not a serious business. But it's, so semantics still has some role to play in logic too. Okay, so this is based on joint work with Olivier Gasquet and François Schwarzentruber. And it's about a particular framework, logical framework, for visual-epistemic reasoning. So I will first briefly introduce the whole idea. I'll give you, oops, sorry. Okay, I will introduce a basic logic, which we named somewhat tongue-in-cheek, of course, Big Brother logic, and you will see why. I will give you semantics, or in fact different semantics, and almost no proof theory, but I will flash some axioms here to just give you a flavor of non-trivial things that one can say in this logic. And then, well, it depends on the time and the eyes of the audience. I'll decide whether I should talk more or less on algorithmic issues of how to solve model checking and satisfiability testing in this logic. And then I will end up with some extensions, future work, and concluding remarks, and say a few more general words about, well, logical reasoning on visual information, or visual epistemic reasoning in general. So, okay. Now, first, some introductory words. So we are talking about multi-agent systems of a very generic kind. So agents learn things in the process of their action, and much of the knowledge that they acquire is based on the visual information that comes their way. And so there is a well-known saying that a picture is worth 1,000 words. I will rephrase it and strengthen it slightly. A picture is worth 1,000 formulae, as you might see later. So that if we want to formalize reasoning with and about visual information, then there are several problems, several challenges that we face. First one is the symbolic representation. We had a chat with Heinrich last night, and we both agreed that there are no inherent reasons why logic or logical reasoning should be tied with symbolic representation and symbolic reasoning. It just so happened. But of course, there are many other forms of logical reasoning. One of them is reasoning or processing visual information. And it's still a challenge how to actually represent this in, or how to translate such a reasoning into the traditional symbolic way. So symbolic representation of visual information, visual reasoning, is still a big challenge ahead. Then, well, okay, so I won't go in details, but probably most of you know about the frame problem. There are too many things in the world, and so, for instance, if you look around and, or you just think of what you are seeing at the moment, you will see that there are way too many things that your eyes see, and if you want to reason about very simple things, like, for instance, what I'm saying and whether it's true or false, then you should be able to ignore most of what you see. Or even everything that you see, you can ignore me too. Just listen to what I'm saying. And so that if you are to record all this visual information and then reason about this, then there will be an explosion of too many things to put there on record. And very few of them will actually be used in your reasoning. So this is the frame problem that comes from AI. Then even bigger challenge is how to actually organize such a logical reasoning based on visual information, and how to combine visual information with knowledge and the interaction between these two. So what I'll present today is something rather modest and simple. I'll present a rather concrete and simple framework where this interaction has been captured in a reasonably satisfactory way, as I hope you agree. So, well, here is a picture of the type of scenarios that I will consider here. So think agents, each one of them, or many agents, each one of them equipped with a camera, well, surveillance camera if you want. That is a vision device that has certain sector of vision in the plane. And of course, okay, so here you see pictures of these agents with their visual vision devices and the highlighted sectors of vision. There can be some objects, obstacles or other objects that they may see or want to see or just see, and so on. So one way of thinking about this is, for instance, a camera surveillance network. And well, again, kind of tongue-in-cheek, we have proposed this application of what we are doing, namely to well, to model and then to formalize reasoning about surveillance cameras. Yes, I'm being on record now, so I'll use this to advertise. I'm still waiting. We are still waiting for a national security agency to come with a 7-digit offer to buy our results and then to implement them. So maybe this record will go the right place. We'll see. But anyway, so of course, take this with a pinch of salt. I will be talking logic here, not applications and not security systems. So the main aim here is to represent and then compute visual-epistemic reasoning of these agents, and I'll make this clear of what that means. Okay, so first some more details about the way we model this situation. So what you see here is several agents labeled with A, B, C, and so on. And then you see this beautiful animation due to Francois Schwarzentrue, these eyes that show particular direction of vision, right? So that each agent would have a current direction of vision and a sector, well, cone in general, cone of vision. So this is illustrated for agent A. So this would be the cone of vision for A, which means that A sees, well, the agents B, C, and E, and A does not see the agent D. Okay, so I hope that's clear enough. So we'll make some general simplifying assumptions, which we assume also that they are common knowledge amongst the agents. In particular, that agents will be transparent points in the plane, so that one can see through an agent. That all objects of interest are agents. That, again, is just to simplify things. I mean, if we can think of some sort of inactive agents or passive agents just to associate with all objects of interest. So that's not really important. Well, again, a simplification, idealization is that agents see the infinite sectors of vision, so they have infinitely long vision. The angles of vision are the same. That's not really important, but it's useful as a technical assumption. And so far, there will be no obstacles in the picture. Okay, so here is a logical language to represent symbolically at least part of the information recorded in these kind of models. So what you see is, okay, first atomic propositions. There are no uninterpreted atomic propositions, that is, no propositional variables. They can be introduced, but they are not needed because things are interesting and complex enough even without them. So this is the only type of atomic propositions which we read as A sees B. That is, the agent A sees the agent B. Then we have the standard propositional logic repertoire. Then we have this, well, dynamic logic style of a model operator, which you can read as follows. So A is the name of an agent, phi is a formula, and this means to say that after the agent A turns around at any possible angle, then phi will be true. Okay, then we have the standard epistemic repertoire. So in the visual knowledge, the agent A knows that phi is true. And then common knowledge amongst the group of agents, that is, phi is a common knowledge amongst the group J. Of course, we can throw in distributed knowledge as well, but it won't play any important role in the talk, so I won't include it here. So some definable operators. So the negation of A sees B, are we denoting this way? And then we have the corresponding dual diamond operator. The agent A can turn around, that is, can turn its camera around at a certain angle to make phi true. Okay. So a few important background references to previous work on which this one heavily builds was work by Schwarzentuber, Balbiani, Gasquet, and yes, those three people who consider somewhat different situation, namely agents can move freely in the plane, but they can only see a half plane, so that the angle of vision is 180 degrees. And then, they have some results which I'll not discuss here, but the main problem that arose there that remained open was to obtain optimal algorithms and to identify, to compute the optimal complexities for model checking and satisfiability testing for this logic, and also to obtain a complete axiomatization for the resulting validities. I'll come back to this briefly later. So the work that I will present here, which was first presented in an AMAS conference paper some year and a half ago, the assumption is that the agents are fixed, so their positions are fixed in the plane, but then they can turn freely around. So that is, again, the metaphor of the cameras. Cameras are fixed, but they can turn around, they can move around. And the angles are generally unspecified. And so the main technical results in this work, which I might or might not present or just mention briefly, are that we have obtained optimal algorithms for model checking and for satisfiability testing. And we have some better idea of how the validities will look there, which I will discuss briefly later. Okay. So before I introduce the semantics for the logic, I need to introduce, of course, the relevant type of models. So I'll start with the most natural models, that is geometric models, that look as follows. So a geometric model is just a tuple of three components. The first one is the position function, which to every agent would associate a position in the plane, which is just a point in the plane. Then we have direction, again to every agent. It will associate a unit vector, which shows the direction, the current direction of the vision of the agent. And then the angle function, which to every agent would associate the angle of vision of its camera. And again, well, we'll assume most of the time, but not necessarily, that all these angles of vision are the same. So this assumption will not be needed for most of what I will say, but still. Okay, so here is a picture. This is the position, this is the direction of vision, and this is the angle of vision. So this closed sector of vision that is highlighted here will be denoted in this way, and I'll use this notation on the next slides. All right, now we want to reason not about just one model at a time, but about the possible variation of models when agents, well, turn around, or in a more general framework, when they can move around. So, and we also want to employ the model logic flavor of semantics here, so that it's a natural extension from geometric models to what we call geometric cryptostructures that look as follows. So suppose that we have fixed the positions of the agents. We have fixed the angles of their cameras. So the only thing that still remains free or possibly variable is that their directions of vision. So that at every moment of time, every agent can be looking at one or another direction, and so that we have a tuple of directions of vision, and there are, of course, infinitely many such tuples. I mean, assuming that the direction of vision can be really any vector in the plane. So we can think of each one of these tuples of directions of vision as a possible word in a Kripke model. And so that gives rise to a geometric Kripke structure that looks as follows. So first, these two components, which again are fixed. And then we have this set of all possible, well, tuples of directions of vision, or we can call them direction functions. And then we have two important relations, both equivalence relations, which will be needed to give semantics of the basic syntactic operators that I've presented here. The first one relates to direction functions. So, sorry, for every agent A, we have such an equivalence relation RA, which relates to directions of vision if they are the same for all other agents. So that is, everyone else is fixed or is frozen, and then the agent A can possibly turn around. That's the idea. And then the other one would be eventually will be the epistemic relation. So again, for every agent A, we have this relation which relates to direction vectors, or to direction functions, if they look the same as far as the agent A can see. And I'll make that clear on the next slide. So again, there were two types of relations. The first are called turning relations. And so, for instance, what you see here is two possible words. This is the one, this is the other one. They only differ by something which is not well visible here. That is, okay. So they only differ by the directions of vision of these two agents. I think that's not supposed to be the case, but so ignore this. Sorry, this is a mistake in my animation. So suppose that these two look exactly the same as this. So the only thing that can change actually is the direction of vision of the agent A. All right. So each one of these, come on, each one of these models is RA related to this one. Again, assuming that these look the same as this. Right. And then the epistemic relations, now they look as follows. So two models would be A related if they look the same as far as the agent A can see. So here is the sector of vision for the agent A, and in both pictures the agent sees the same thing. Behind the agent A there are different things. That is, well, the other agents that A cannot see, they can look in different directions. So that, for instance, they can change their directions of vision, but the agent A does not see that. So that these words will look the same for the agent A, and that's the standard way that would model the knowledge of A. Well, at least the immediate knowledge that comes from the visual information. Okay. By the way, if there are any clarification questions, feel free to ask me during the talk. Okay. So now I can give you semantics, and the semantics is pretty much standard model logic semantics, Kripke semantics, based on these geometric Kripke structures that I've introduced, because for every syntactic operator we already have the corresponding semantic relation in the model. So first, the atomic propositions. A sees B is true in the world W precisely when B is in the sector of vision of A, as you would expect it. Okay. Then A knows that phi is true. Well, again, this is the standard way we would model knowledge in epistemic logics. A knows that phi is true if for all that the agent A knows, that is, in this case, for all that the agent A can see, phi holds. That is, phi holds in every world that the agent A cannot distinguish from the current actual world. And so formally, that means phi must be true in every world V. Sorry, ignore this, it's a leftover. Phi must be true in every world V, which is A related to W in terms of the epistemic relation, which I presented. Okay, so this is the semantics. Well, I haven't given you the semantics of the turning operator, and now I realized again that it's somehow disappeared from my slides. It should be there, but it's not visible. So the semantics for the turning operator operator. It looks exactly the same, but now we are using the other relation, RA. That is, after the agent A turns around, phi would be true if at every word that can be obtained from the current one by just turning the agent A's direction of vision, phi will be true. So again, it's the standard model logic semantics that you would expect to see here. Sorry. Okay. Now, so these models are very intuitive, very neat and nice and natural. However, they are not quite suitable for practical purposes, namely for computing this reasoning, because they are infinite models. A geometric Kripke structure consists of infinitely many possible models because there are infinitely many possible tuples of directions of vision for the agents. So that if we want to do, for instance, model checking, then we have to, well, at least theoretically go through each one of them and check whether the formula is true or not, which is not feasible. So that, as usual, in order to represent the problem as an algorithmic problem, we need to finitize it. We need to find a finite abstraction of the actual type of models that we are considering. So that what I will present here is finite abstractions of these geometric Kripke structures, which we'll call vision-based models. And the idea, again, is very, very simple. So here is a picture. Here is a geometric model. So it's one possible world. And suppose we fix all other agents and we only let the agent A turn around. So as the agent turns around, it kind of scans the environment, right, 360 degrees, then in different positions, the agent will see different sets of other agents, or objects of interest, in general speaking. And so we can actually compute and record them one by one, and so this is what we'll be doing now. So at the moment, the agent A sees nothing, no one. So that's the empty set. This is one of the vision sets for the agent A. As we start turning the agent around, then at some point, it will start seeing the agent C and nothing else. So this is another vision set, and so on. So again, there is empty set. Then, okay, at this moment, at this position, A sees D. Then, okay, A sees D and F. Then at this position, we'll see, trust me, with the angles, D, F, and E, and so on and so on. So that we can record all the possible vision sets for this agent as we turn this agent around. And you can think that the agent has first, before the whole story plays, has scanned the whole environment so that the agent knows all these possible vision sets for herself. Okay. And then we can do for every agent. And in fact, that can be computed quite easily, because notice that there are only linearly many positions in which the vision set will change, or actually roughly twice the number of agents. Okay, so that all these vision sets for each agent can be computed quite quickly, and so that eventually we can obtain what we call a spectrum of vision of this geometric model. So that would be all the possible tuples of vision sets for the different agents. Okay, so now, given such a spectrum of vision, and in fact can be abstractly given, it need not be computed from a concrete model. Given such an abstract spectrum of vision, we can define a vision-based model, which again will have a Kripke structure flavor. It will be actually a Kripke structure that looks as follows. So the set of possible worlds will consist of all possible tuples of vision sets, one per agent. Again, you take a snapshot of a reality, you take each of the agents, look at what this agent can see, and then put all this in one tuple. I'll show this on the next slide. And that will give you one possible world. And so that lets each of the agents independently turn around and see different vision sets that would produce a set of possible worlds. But a finite set, because every agent has only finitely many possible different vision sets. Okay. And the relations which I present here, they are sort of natural abstractions of the two relations, the turning and the epistemic relations that I introduced earlier, so that I will not torture you through the details, but trust me that it's just an abstraction that is, well, quotienting of those relations down to the vision sets. Okay, so here is a picture. Well, what you see, again, what is missing on the animation is the sectors of vision of the agents, but you can draw such sectors of vision so that the agent A will only see, where is A? Will only see B, and B will only see C, and C will see nothing, and then D will see E and F, and so on. So this will give you one tuple of vision sets, one per agent. And that tuple will be a possible word in this vision-based model. And again, there are only finitely many such tuples, so that the vision-based model will be finite. And it should be intuitively clear that it records all the necessary information that we need in order to evaluate truth of formula in our language. Okay. So that we can now transfer the semantics, or, well, reduce the semantics from geometric Kripke structures, which are, again, infinite, to their finitary abstractions, namely vision-based models, in a way that you would expect, again, not going through these technicalities, but you can take this as a simple mental exercise to see how the of the turning and the epistemic relations will be reduced down to these vision-based models. Because after all, this is all that we need. When we compute whether an agent knows something, then we don't need to take into account the full geometric model, all the geometric information. We only need to take into account the vision, the current vision sets of the agents. And so again, this is a simple, but it's a fundamental idea. This is how to abstract away, how to solve ad hoc, on the fly, the frame problem. Abstract away from this infinite, potentially infinite information that comes our way, and then use only a finitary fraction, a finitary portion, a finitary abstraction of it, so that we can really do effectively, algorithmically, if you want, do reasoning. Okay. So, a few words about the expressiveness of this language on the semantics that I've introduced. Actually, well, I introduced several semantics, well, 3 semantics, on geometric models, on geometric Kripke structures, and on vision-based models. But it should be intuitively clear that these semantics are reducible to each other, so that we can talk about one semantics represented in 3 different ways. Okay. So, a few words about the expressiveness. You will see that it's actually fairly expressive language, and one can say fairly non-trivial things. All right, so to begin with, one can relate in a very natural way knowledge and vision to begin with. Well, and now this is not a postulate, it's something that you can compute from the semantics, that an agent knows that he sees what he sees. And sorry, my agents tend to be males, but that's by no way a statement of any, actually, I should say it, I'm not sure. Okay. So an agent knows what it sees. Sorry, an agent knows that it sees what it sees. Okay, that we can record with this formula, and it is actually valid in this semantics. But also, an agent knows that she does not see what she does not see. And then again, this can be recorded this way, and it is valid in this semantics. But there is more than what meets the eyes, and now I say this in literal sense. That is, there is more in the knowledge than what can be immediately derived from visual information. And this is where things become really interesting, because it was just, if it was just mechanically combining what you see and what you know, and then it wouldn't be too exciting to give a whole story here. There is more to it. So I'll just give you a little hint of why that's the case, because there is a geometry behind in the background. So for instance, a very simple thing. See, suppose that A sees C1 and A sees C2. And that, by the way, is common knowledge, so all agents know this. No, I'm sorry. That's not a common knowledge. Ignore what I said. Suppose that A sees C1 and A sees C2, and suppose that the agent E is in between C1 and C2, between in geometric sense. So the point where E is positioned is between these 2 points. Now, this fact is common knowledge, because, again, every agent knows the position of all others. So then, for the agent A, we can claim that A knows that if any other agent B sees C1 and B sees C2, then because of the, well, geometry of vision, that is, the vision sector is a convex area, then B would see everything that's between C1 and C2. So in particular, if it so happens that E is in between them, then B will see E. Now, so suppose that A doesn't see B. So A can't tell for sure what B sees and doesn't see. But A can compute some knowledge about what B can see or does not see based on simple geometry. In this case, it's really very simple geometry, but then one can generalize a bit. So I'll not go into this. Okay, now here is a more complex example. It's just an example of expressing things. So I'm not claiming that this is valid or even satisfiable, but you might actually want to sort of play around mentally and see, make your mind whether this should. Let me read what this says for you. So it says that if agent B sees A, but not C, and knows that A can turn around so as to see both B and C, then B considers it possible that A knows that B sees A but not C. Okay, so it's just a demonstration of expressiveness. So you can say really sort of unobvious and subtle things in this language. Okay, moving on. What is certainly more interesting is that one can express some important geometric relations, and those of you who know the early work of Tarski and followers on well, axiomatizing foundations of geometry, they would appreciate the fact that one can express in this language collinearity and then betweenness as well. So for instance, again, A, B, and C are three agents, but you can think that something is wrong?
No. Cold.
Oh. Shall I warm you up with some exercises? Turn around, see something, reason about that. Okay. So, right. Now, the point is this. This formula, which says whichever way the agent A turns around, if A sees B, then A will see C. If you think a bit, you realize that can only be true if A, B, and C are aligned. That is, well, A sees B and then C. They are on the same line, so that whichever way you turn around, that would be the case. And that's the only possibility, the only case this is if and only if. So this formula expresses the fact that B, not just that A, B, and C are collinear, but that B is between A and C. And so that we can actually use this to express the betweenness of one point between two other points by saying it both ways, from the perspective of A and from the perspective of C. So we can express betweenness. And that means a lot. Again, I won't go in more details, but having betweenness, you have a lot. Yes?
What's the problem there?
Well, there is no particular problem, but the point is that having betweenness, so if you can express betweenness, then you can say a lot about the geometry. And, well, in fact, if you have betweenness plus a bit extra, then you can express just about every elementarily definable geometric relation. So that's what I was referring to, but that's... Sorry? What does that mean? Right. So, as I said at the beginning, one of the simplifying assumptions is that agents are transparent points. That need not be the case, and if you make them non-transparent, then things will change, but in a controllable way, so that this issue does not arise there. Okay. So. Now, again, some flavor, some examples of validities here. I will say from the outset, we do not have yet a explicit complete axiomatization, and you will see why, at least because there is no unique axiomatization. It would crucially depend, as you might guess, would crucially depend on the angles of vision. So for simplicity, again, assume that all agents have the same angle of vision alpha. And so, for instance, take this formula, C, A, B, C, which roughly says that each of the agents A, B, and C sees the other two agents. So this is only realizable, that is satisfiable, if the angle of vision is at least 60 degrees, pi over 3. Think of this. There's some of the three angles in the triangle is. Okay. So that this formula, whether this formula is satisfiable or not, it actually depends on geometric assumptions that are behind the language. behind the semantics. Or otherwise, if we have n agents, to say that each one of them can see the others, that means that they must be arranged in the vertices of a convex polygon of n vertices. And so, again, assuming that their maximal angles of vision are all equal to alpha, that can only be done if alpha is at least that much, which is the angle in the regular n vertex polygon. So, okay, again, somewhat non-trivial validities that arise here, or non-validities that depend on geometric assumptions. Something different, again, so suppose we have a bunch of agents A1 to AK, right, and then a bunch of other agents, which are many. Okay, how many? Doesn't matter, but if you take the agents A1 to AK, and for each one of them, sorry, I did not say this. This is the case when alpha is pi, that is, every agent can see a half plane. So this is probably the simplest possible case, and yet it's already non-trivial, as you will see. Because, again, so take the half plane, that is, take the line that determines the half plane for every agent of A1 to AK, and know the plane. So in general, they will determine a number of regions in the plane. They will partition the plane in a number of regions. And in the most general case, this number would be somewhere that much. So that if you have more than that many agents, C1 to C something, then by the pigeonhole principle, at least two of them will fall within the same region. That is, they will be equally seen or not seen by each of the agents A1 to AK. And so that you can say in this simple formula. So again, this is a simple claim, but it involves some non-trivial geometric combinatoric fact that's behind the semantics. So it doesn't come from logic. Okay, and so on. So basically, to sum up things, depending on the angle of vision, there will be many, in fact, infinitely many possible cases. And even in the simplest case, where the angle of vision is pi, you can't axiomatize this logic with finitely many axioms. So it's infinitely axiomatizable. But okay, don't worry, it is decidable, if you will see. So that, well, there is a recursive set of axioms, but still finding explicit, even though infinitary, but explicit sets of axioms is yet still an open problem. Okay, so let me see, how am I doing time-wise? I should try to stop, let's say, 10 minutes before. Yes, so 10 minutes before 10 would be good enough. Okay, so now what I will do is I will formulate the two main logical decision problems that we consider, namely the model checking and the satisfiability testing. And I'll just hand wave how we solve them and the main results. So I won't go in technical details, assuming that only probably a small portion of the audience is hardcore computer scientists that would be interested in the intricacies of the precise complexities. So, okay, the model checking problem is defined as you would expect it. So we can define it in terms of the most natural models that